Hello, Mr. Hine, and I am back. This video is going to cover 222 and 223, and it is going to cover one of the big topics of calculus. Um, this one is big. I can almost guarantee that they're going to ask several AP exam questions on it. If you take the AP exam, there'll be a free response question on it, or there'll be some incorporation of this in a free response question. All right. So, continuity. Give this 4 stars of importance. Very big. Not the biggest, but very big. All right. Now remember that the informal definition of continuity of a function is continuous is we said a function f is continuous if you can draw the graph without lifting up your pencil. Lifting your pencil. And that was kind of our informal definition of continuous. We also use the word connected. All right. Connected being kind of a nice word. So if I make a graph here, and the graph looked something like this. This is continuous because it's connected, no matter what interval you look at. Now remember that continuous, hopefully you guys notice, continuous does not mean it goes on forever. It does not mean it goes on forever. That's what my freshmen always like to think. And I could see why they get that. If something's continuous, you think that it's continuing on. But math comes from, Arabic, and then Arabic was converted, and how the Romans interpreted it. And it's kind of gone through Latin and other languages, and as it's come to the English language, continuous just happens to be confusing with the language we know it as well. So a function f is continuous if you can draw the graph without lifting a pencil. That was our informal definition, such as this. So it's continuous on any interval here. It's connected. Right? It's continuous from here to here. We could draw that. It's continuous from here to here. We could draw that. Right? But now, what's the formal definition? A formal definition. Right? And this formal definition is very important. This is the 4 stars. All right. A function f is continuous if and only if, and there's 3 conditions. Say these 3 conditions with me. Memorize these 3 conditions. They are big. If the limit as x approaches some value a exists. All right. Second one is if the value if the function at that value exists. And the third one is if the limit is equal to that value. And that is the formal definition of continuous. All right. And that is huge. Anytime you want to prove continuity, so if it ever asks like, is this function continuous on a to b? Is the function continuous on some interval a to b? You would have to prove all 3 conditions. It's not good enough to just jump to the third. Right? It's a logical progression of 1, 2, 3. Where 1 and 2 can be interchangeable, but 1 and 2 have to happen for the third to happen. And now let me go into what these mean, and this will make a little bit, hopefully, more sense to you. All right, so I'll make a graph here. Hopefully don't go too far over where my face doesn't get in the way. I'll go 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6, 7, 8. And I'll make a graph that does something like this. All right. So say we have a function like this. Very strange one, but it will work. All right. Now, let's see. If the question says, example, is this continuous at, say, x equals 5? All right. So let's go through our conditions. So the first one is, what's the limit as x approaches 5 of f of x? All right. And now, in order to show it exists, remember that you have to show that the left and the right equal. So in order to show this, you're checking what's the limit as x approaches 5 from the left, and you're checking does that equal the limit as x approaches 5 from the right. All right. That's the only way the limit exists. So as we approach 5, here's 5. As we approach 5 from the left, then we're on the curve here, approaching 5. We're approaching the y value of 3. So as we approach from the left, we're approaching 3. On the right side here, we're approaching 3 as well. So good. The limit as x approaches 5 of fx is 3. Okay? The first condition is checked. The second condition, what's f of 5? Does that exist? So f of 5 is, where's the function at 5? At 5, the function's here. Here's your closed circle, which is at 3. Okay, that's condition 2. Does it exist? And then the third one is, are these the same? Is the limit you found equal to the value that it's at? In which case, they're both 3. So yes, the limit as x approaches 5 of f of x is equal to f of 5. They both equal 3 here. So thus, f is continuous at x equals 5. And that's how you would answer that, is you have to go through all 3 conditions. If you only went through 1 and 2, or you jumped straight to 3, you would lose points on the AP exam because there's no logical flow. I mean, in order to get to the third condition, which is the most important condition, you have to prove 1 and 2 first. All right, what if we came over here, and I'll use red for this example. Using the same graph, is this continuous? And by the way, before I go to that, notice it makes sense because at 5, we can continue drawing without a pencil. Our informal definition holds true. We never had to lift the pencil. Okay. So, what am I doing? I don't need to draw a graph. Let me refocus that. What is it continuous at x equals 3? All right. In which case, you might already know that the answer is no. Because at 3, we can't keep drawing with a pencil. But now you have to prove it using calculus and definitions. You can't just prove things by saying, look at what it does. Right? We have to use the definitions that are agreed upon. Definitions are huge in math. Right? So let's go through the order and see what happens. So the first one is, does the limit as x approach 3 of f of x exist? That's the first one. All right. Well, the limit as x approaches 3 from the left is equal to, as we approach 3 from the left, we're on the curve here, and we're approaching 3. And as we approach 3 from the right, we're on the curve here, and we're approaching 5. And there you go. In which case, this does not exist because 3 is not equal to 5. Now, that's not necessarily the best way to put it. It'd be better to say the limit as x approaches 3 from the left does not equal the limit as x approaches 3 from the right. That's a much better answer here on why it does not exist than my lazy way of saying 3 does not equal 5. Okay? And that's how you would say it's not continuous at 3, because it fails this condition. Fails condition 1. All right. And I don't really like the word 1, but it fails the condition above that I wrote. That's better. We want to be specific. Now, just heads up, what is the value at 3? You could say here, f of 3 is equal to 5. So condition 2 is met, but condition 3 is not met. All right. Now let's go to the back and look at examples, because again, this is a huge concept. I want to make sure you understand it. So I'm going to flip it over. Oh, that's old work. All right. So examples where each condition fails. Okay. So going through it again, remember the three conditions. Condition one is that the limit exists. So as you approach from the left and right, they meet at the same point. The second condition is that the function at that value a exists. And then the third one is that those two equal each other. It's the equal f of it. And those are your three conditions for continuity. So we saw in the back when condition one fails, but here's another one. So condition one fails. Right? Is if we had a graph and the graph did something like this. Right? And you can see right away you had to lift up your pencil. I had to lift my pencil, so it's not continuous. But why is that? Is the limit as x approaches 2 from the left is equal to 2 here, which is not equal to the limit as x approaches 2 from the right, which is equal to 3. Okay. So that's where condition one would fail. The limits don't meet up. Now, what's an example where condition two would fail? Okay. So condition two fails would be a graph that looks like this. Right. Where you have a hole on the graph, because condition one, the limit as x approaches 2 is equal to 2. As you approach from the left, you're at 2. As you approach from the right, you're at 2. But, oh, no. I'm sorry. This would be condition 2 fails, is that graph. But f of 2 does not exist. There's no value for the function at 2. There's a hole in the graph. Okay? What I did actually, the next one, is I jumped the gun. That is when condition 3 would fail. Is a situation where the limit exists. There's a value of the function at that point. Right? But those don't equal. So condition 1, the limit as x approaches 2 is equal to 2. Condition 2, it's my dog. Condition 2 is f of 2 is equal to 3. There's a value right there. That's good. But condition 3 is the limit as x approaches 2 does not equal f of 2, because the limit as x approaches 2 is equal to 2, but f of 2 is equal to 3. These don't equal each other. And that's where condition 3 would fail. All right. In my final example, I'd say is like in my Starbucks example, it would say you and a friend want to meet at a Starbucks. Well, condition 1, the limit, would be that you both approach the Starbucks from different locations, right? And you have to approach the same one. For a function to exist, is the Starbucks has to exist. You can't just end up going to a spot. You can't meet at a spot and be like, oh, wait, this is a gas station. This isn't a Starbucks, in which that failed. So there has to be a Starbucks there. And if all that happens, then you can enjoy a cup of coffee, right? You meet at the same point. It exists at that point. So, hey, enjoy your cup of coffee, right? Hey, wait, but you shouldn't be drinking coffee. You guys are too young still. Just kidding. They would always say that to me too. But Everyone's different. So there it is, very big. Know what it means to be continuous. Know that you have to prove these three to show continuous, which is what I have. Again, I'm going to leave it on this as my final point. All right, right there. A function f is continuous if and only if the limit exists, the function at that value exists, and the limit as you approach that value is equal to the function at that value, and thus you would be continuous at that point A. So a function is continuous for that. Hope that makes sense. If not, definitely ask on it because it's one of the biggest concepts. It's so far probably, I'd argue, the biggest concept this year so far. All right. Good luck.